All right, thank you. I'm going to preface this talk with the fact that I came prepared to present a poster at this conference, but due to some scheduling changes, I was able to speak to you today. So I last minute threw together some slides, but I encourage you to check out my poster, poster number 52, after this if you have any questions or want to talk about this further. All right, I'm going to jump right into it. Near-field spectroscopy is a useful technique because it has a high signal-to-noise ratio and a small spatial resolution, which can produce really easy analysis of mineral identification and organic identification. But it does pose challenges because of strong probe sample interactions in the near field, which makes the spectra look different than what we're used to with far field spectroscopy. So our study here sets out to find a link between near field and far field spectroscopy to make future analyses easier, specifically for possible sample return missions to be able to analyze those samples and possibly compare them to remote sensing analysis. So these are our samples that we use for this particular research. We have 6 glass samples with varying silica weight percent. And we chose glasses because they are amorphous, so we don't have to worry about orientation effects. And they have very few spectral features, so comparisons in the near field and the far field are fairly easy. There are also lots of planetary applications for glasses, including lunar glasses, glass chondrules, volcanic glasses, etc. So getting into the results, this is a plot of the phase, which is comparative to transmission data of our near field analyses of our glasses here. As you can see, all of the glasses are in agreement. You can see a peak right in the middle there at around a wave number of 1100. And we have our amplitude data here, which can be compared to reflectance data. And again, all the glasses show a decent agreement with a notable peak at a wave number of 1000. So I've plotted that same data here against far field micro FTIR spectra. And as you can see, there are some notable differences. This is caused by the sample probe interactions. So the dotted line data is the far field and the smooth line data is the near field. And the main differences that we notice is that the near field data has a more well-rounded peak that happens to be at lower wave numbers, and we have a more defined narrow peak, as well as a little bit of a hump towards higher wave numbers in the far field data. This is a plot showing how the silica weight percent it relates to the peak positions. So in both the near field, which is the yellow data, and the far field, which is the purple data, we notice a general trend that with higher silica content, the peak position is found at higher wave numbers. So from this data, we can try to actually find this link, which is done by calculating optical constants. We have robust methods for calculating optical constants in the far field, but unfortunately with the near field data, it's a little more complicated because we have trouble finding an acceptable quantitative predictability with the current methods that are used. So reviewing several possible methods to calculate optical constants, we have chosen 3 possible methods to dive into, one of which we have begun developing and I'd like to show today. The other 2 are hopefully going to be worked on in the near future so that we can compare the optical constants and try to find this link between the near and far field data. So those are the reversed finite-dipole model, a conformal mapping method, and a generalized spectral method. So the reverse finite dipole model is what I have to share with you today. But the main difference between these three models is the shape that we approximate the tip. So for the reverse finite dipole model, we approximate the tip as a spheroid, but for the conformal mapping method, we would estimate it as a cone. And for the generalized spectral model, we would approximate the tip as a prolate spheroid. So this is just one of the glasses that we have calculated optical constants for. The blue data being our near field calculations using the reverse finite dipole method, and the orange being the far field. And as you can see, we do have some general agreement in the shape and a decent agreeability in terms of the range, but they are not exact. And we do hope to not only fine tune this model, but investigate the other models, this being the most simple of the three, to hopefully come up with better calculations for these. And so here's just a general summary. I didn't make a slide for future work, but we also hope to soon investigate how orientation effects can play into this research. And we also have a new basalt sample that we hope to add to these glasses to provide another example of a glass with a lower silica weight %. So thank you.